Alright, so the first problem I'm going to be doing is 5.57. Now the first part is to write down the formula for the acceleration. So we know that the acceleration is u times our velocity field vectored partial derivative of x, and then the same thing in the y direction. So we have v dv and then over dy. And then in this problem, our velocity field vector is not dependent of time, and it's also not dependent of the z direction, so I just won't write them down. So now here what I can do is write down the actual velocity field. So Vax minus b in the I direction, and then minus Ayj. And then we're also going to write the u and the v component of our velocity field. So the u component is just xy minus b. Notice that I don't put the unit vectors I or j there. That's because they're already in that direction of u and v. The next step is to write the partial derivatives too. So we have our partial derivative of velocity field v by x, and that's just going to be ai. And then our partial derivative of our velocity field by y is going to be minus aj. Now the last thing to do is to kind of just put this all together, and then we can finally obtain an expression for our velocity, for our acceleration as a component of x and y. It's also important here to not to forget that our acceleration has a y and an x component, so that's due to the partial derivatives. You see how the y and the j component stay there, which means our acceleration is also going to have a y and a j component. Now we can also evaluate our acceleration at a certain point, x and y, so in this case at 0 and at 4/3. And then in here we're just going to replace by our known values. So we know that a is 0.2, b is 0.6, and then x is going to be 0, and y is going to be 4/3. So now for the next part of the question. This question asks to find the streamlines. So the formula to find the streamlines is the derivative of y over the derivative of x for a streamline is equal to v, so the y component of our velocity field, divided by u, or x component of the velocity field. So in this case, it's going to be dy over dx is equal to minus ax over ax minus b. And then what we're going to want to do is do separation of variables to be able to find the expression for a and as a function of a and y. So here I'm going to integrate by both sides, where I'm going to get this expression here, and then I'm just going to be doing some basic algebra with a little bit of tricks from the exponents, so exponent rules, to be able to find this expression. And so here we get the final expression, which is c is equal to ax minus b, which will be used when we want to plot the velocity fields in MATLAB, which will be the next part. All right, so welcome to the last part of the kind of this problem, which asks us to show the acceleration vector on a streamline plot. So I have the solution right here, and we solved up to the point where we have our streamline function. So the next thing to do is to kind of plot this out. So what we can do is I'm going to open up, what I have open up to the side here is Octave, and we can get started at this. So first things first, we're going to declare some variables. So we have our variable a, which is 0.2, and our variable b, which is 0.6. All right, and then we also want to define a space. So this streamline plot is going to sit in an xy plane, and these x and y values here are going to take different values for c. So what we want to do is declare a linear space for x, and we'll say, let's just set it to minus 10, 10, and actually we'll define these steps as, let's say, 10. So that, and we'll do the same thing for y. So now if we run this, we're going to print out x and y right here, a linear space, and we should be able to see, so if I run this, should be able to see in the command window right here. I'll just clear that window, rerun it. You should be able to see, so x holds these values from minus 10 to 10, and y holds these values from minus 10 to 10. So the next part to do this is that this plot is going to be on an xy plane. So the way to do that in MATLAB is 2 y equal to mesh grid x, y. So now I'm going to comment out this. What we should see right here is our output of our mesh grid instead of just the xy plane. So what this is essentially is that we're going to have one coordinate, and it's going to be minus 10 for x, minus 10 for y, and then our next coordinate here, our x will be changing, but our y will be staying the same. So you can kind of visualize that as if we're sitting in a plane here. Actually, right here. So if we're sitting in a plane, we'll be traveling in the x direction, certain ticks, and the y will be staying constant and we'll be moving. So essentially what it's doing is it's lying down this mesh for us. Alright, so now that that's done, what we can do is plot or streamline. So that would be C, Y. Now we have to use, remember to use this operator, A times, so actually we don't want to use small y here, we want to use big Y, because we're setting these coordinates according to the mesh grid. So same thing, dot x big Y minus b. So now if we run this again in steps, we should see that C now takes these values. So C would be, so this x and this y would replace in here, right there. So that'd be 2 minus 0.6 times our y right here, which is minus 10. Sorry, so there's another minus right there, which we get this first C. So the last part to do is to plot the contour. We do that with this little nice little function here, contour C. I think this will give us our contour plot right here. So this image isn't super nice, but we can actually make this a little better. So one thing that we can do is plot a little bit more streamlined. So I think if I do 10 here, the next argument, let me close this. Yeah, we can see a couple more streamlines. So if we put this up to 50, so now that's looking a little difficult to read, but we can see that we're plotting more streamlines, and then we have our x-axis and our y-axis, and we're seeing that these values take, depending on where we lie on this axis, we have a different, we're lying on a different streamline here. We'll just switch this to 20, and what we can actually do is copy off the MATLAB website a quick, useful, we can actually plot what is the values of the contour lines by using this. So show text on, we'll run this, and we can actually see the values of the contour plots here. So they take different values depending on where we're sitting on in this line. So now the final step here is that we also, if we're sitting on a spot, let's say in x and y, well, we have this acceleration. We know that this acceleration, we defined it for a couple problems here. So up here we found the acceleration for at the point 0 and x is 0 and y is 4/3. So if we go here at x0, we can scroll out here a bit. Why is it not trying? Oh, I know why it's not showing. It's not showing because when we plotted the contour here, what we also want to do is plot this x and y value with the contour so it actually defines it. So now if I run this, there we go. Now we get something that makes a little bit more sense here. So we have, as we're varying in x here from -10 to 10, varying from y from -10 to 10 right here, and we looked at the acceleration, so x is 0 right here, and about right there, we're kind of hitting this contour somewhere along here, and we want to figure out, well, what is this acceleration? Well, we have the formula down here. Sorry, up here, which is this formula right here in vector form, because we'll have an acceleration and an x component and a y component. And now what we can actually do, I can define the x component of the acceleration as being a, again, dot product with or x minus b times a, and then or y component over acceleration to be a times a, and then again times y. Again, I'm using the big x's right here because it's part of our grid. So now that our acceleration components are set up, what I could do, I'm just going to put hold on, and a quiver plot in MATLAB lets you plot these arrows on the plot, so we can actually see where these vectors are going to lie depending on the xy component. We're going to have these xy. We're going to plot ax and ay. We'll do hold off. We'll run that. And as we can see here in our plot, not only do we have the streamlines, but we also have where the acceleration is pointing. So again, on that problem where we were looking at acceleration is 0 and over 4/3. So right here at 0 and about 4/3 right here, we seem to be pointing in that direction, which seems correct because we have a negative x direction. We're pointing negative in the x direction. We have a positive y component here, and we can see both these components are quite small. As we go further down here, we get pushed away a lot further as our acceleration grows.